Last time we talked about Oxy-Fuel Cutting, and I mentioned that it eliminates the boundary layer by formation of liquid oxide. And by eliminating the boundary layer, you go from 10 to the third to about 10 to the fifth watts per square centimeter, almost 2 orders of magnitude, about a factor of up to 10 to 50 times greater heat intensity on the surface. Now, when you're making that cut, you actually have to ignite a little spot on the surface, and I mentioned you're basically just igniting the little spot, which is what we call the kerf, K-E-R-F, which is the width of the cut that someone was asking about before. The narrower the kerf, the narrower the cut. But you actually are burning that little surface area, and it doesn't have a depth much greater, the hot zone doesn't have a depth much greater than the width, except that burning hot zone drills a hole. It just burns straight down very rapidly, and the higher the heat intensity, the faster it will burn, because you have to get everything to the combustion temperature, which is around 1300 degrees centigrade.
By increasing your heat intensity, do you get a corresponding reduction in your heat affected zone?
The heat affected zone is determined more by the kerf, the width of that cut, than anything else. A big wide cut, you got lots of heat in there from all the burning oxide. You know, you burn more metal, more heat, which means more heat diffuses off to the sides. So it turns out when you're going at very high speeds, and you are going at high speeds here. Remember when I put this thing up, I talked about speed of welding, and it goes up to 1,000 inches a second over here, and only one inch in 10 seconds over here. The speed goes actually like almost the square of these heat intensities. Higher heat intensities means you go faster. If you go faster, you actually get to the point where the heat affected zone grows on cooling, not on heating part of the cycle. Okay? If you think of the metal, it starts off cold, it heats up, and then it cools down, right? Well, somewhere around between 10 to the third and 10 to the fourth, the heat affected zone is formed on heating part of the cycle, and so therefore the width of the heat affected zone is controlled by the heat intensity. When you get above 10 to the fourth, the heat affected zone is really controlled on the cooling part of the cycle and the width of the liquid metal that you've got trapped in there. Well, in oxy-acetylene cutting, you're blowing liquid metal out, and you've only got a narrow little band of liquid metal, so you actually end up with a narrower heat affected zone. But the size of that heat affected zone is dependent on how big this band of liquid is, and the bigger your kerf. If you're cutting something 36 inches thick, you're allowed to end up with a half-inch kerf of slag left on there. Okay, that jet, which may be an inch in diameter, doesn't blow it all away. If I've got a very narrow jet and I end up with a kerf that's, you know, 1/1000th of an inch, then I get a heat affected zone that's 1/1000th of an inch. Okay, so on cooling, it's the width of the liquid that's left on the surface that heats up the metal on cooling. On heating, it depends on how long you're sitting there for the heat to fuse in. So if you actually go to my little 4-page paper on heat flow and welding, it discusses that briefly. So there's a lot of people say, oh, if you go to high heat intensity processes, you can get rid of the heat affected zone. No, you can't. Did I tell you about the only material I've ever seen that didn't have a heat affected zone? I don't think I told you this story. So I was out at Lawrence Livermore National Lab back in the mid-'80s. One of my doctoral students that come from Lawrence Livermore, being sponsored by them, and John still works at Lawrence Livermore. But anyway, he was being sponsored by them to do a thesis, a doctoral thesis at MIT, and so John was back there, and they invited me to come and spend the day. And wherever I would go, they always had these little signs, like they have, you know, the little A-frame signs in front of a restroom that says, you know, cleaning the restroom. They would say, uncleared visitor today, okay, because it's a nuclear lab, right, or a nuclear lab. And I was kind of read it as unclean visitor, right? But wherever I would go, they'd have these little signs. And I'm there, we're talking about, we'll talk later about convection and liquid weld pools, but I had done some work on convection, and they were asking me about some processes they had for enriching uranium and stuff, and I knew that that's what they were talking about, because you can read that in the literature. But then they showed me something, and they showed me an interesting weld pool pattern. It was an arc weld, but the material had no heat affected zone. And I said, what material is this? and they didn't answer me. They just kept talking about convection. And a little bit later, I said, "What material is this?" And they ignored me again. And finally, we finished our discussion. I said, "What material is this? It has no heat affected zone." And they said, "Well, it's plutonium." Okay, it was just a picture of plutonium, but they had arc welded on plutonium. Plutonium has a thermal diffusivity that is worse than ceramic. Okay, it's K over rho C sub P, thermal conductivity divided by the density. Plutonium is pretty dense, and so it has a thermal diffusivity of about 0.02 centimeters squared per second, which most ceramics insulation are like 0.05, you know, ceramic brick, insulating fire brick or something. And so there is no thermal diffusivity to speak of to carry the heat into the heat affected zone. And so plutonium, and you look at the picture, it just didn't have a heat affected zone. Okay, you didn't have big grains or change in structure. So all of you, they're busy welding plutonium. Okay. But I mean, I always thought it was kind of interesting. Plutonium has no heat affected zone, but that's because it has a very, very low thermal diffusivity. Okay. But as you go to higher heat intensities, things get smaller heat affected zones, but they don't go to nothing. So we eliminate the boundary layer, and remember the boundary layer is formed by these. In oxy-acetylene cutting, you basically would have the oxy-fuel gas, which is now converted to carbon monoxide, carbon dioxide, water vapor. It hits a surface, and then it forms a boundary layer on the surface of these non-reactive gases. But in oxygen cutting, you heat up the sides, and then you blow oxygen straight through. That oxygen doesn't form, I mean, the gas in the oxygen, it's pure oxygen, forms a liquid phase, which means it contracts by a factor of, remember last time I talked about a cubic centimeter water, liquid water, and converting to steam, what's the volume expansion? And I said a good rule of thumb is about 500, it might be 800, 500 to 1,000 at room temperature. In any case, this room temperature oxygen blowing through here is going to condense by a factor of 500 to a liquid phase. So all of a sudden I have no boundary layer. There is no gas. I'm consuming the oxygen. So now I don't have this boundary layer limiting my heat transfer, acting as an insulating layer, and that means I get heat intensities that are near 100% efficient in terms of burning through there. And I actually am burning the iron. And because I'm burning the iron, and the iron is the fuel, it really doesn't matter whether I use that torch acetylene or methylacetylene, which is this matte gas, which is no longer made, or propane, C3H4, or propylene, which is C3H6. Okay, it really doesn't matter which one I use, because I'm just using those to preheat the surface to get it up to the combustion temperature. Once I'm at the combustion temperature, now I'm going to hit it with pure oxygen, and I'm going to combust the iron, and who cares? I can turn those flames off. In fact, that's exactly what you do in a steel mill. You don't have the preheating flames. The steel's already hot. You just hit it with a jet of pure oxygen and burn right through it. So the type of gas you use is not going to limit your productivity when you're cutting. And so there's debates in the literature. Should you use acetylene or matte gas? And my answer is it depends on what you're doing. If you're welding, I've showed you that acetylene will give you 36% more heat transfer through that gas boundary layer because of the higher temperatures. T squared is higher. So acetylene gives you better productivity by 30% compared to matte gas if I'm trying to melt steel. If I'm trying to burn steel, it doesn't matter. Sometimes they use kerosene to ignite the steel. Okay? It doesn't matter. You just have to get it hot enough to get to the combustion temperature. Once you get to the combustion temperature and hit it with the oxygen, you can turn the preheat flames off. They're just going along for the ride at that point. Okay? So in my lab, we have oxy-acetylene tanks if we're welding, and we have matte gas tanks if we're cutting. The cutting setup, we use matte gas because you can store more of it. In fact, now I have this big tank of matte gas that they no longer make. Right? Sell it at a premium somebody has to anyway, so iron is the fuel in oxy-acetylene cutting. Now, There is an excellent paper, it's an ancient paper. Ancient means it was written just after I was born, but before you were born. Which you have, called The Iron Oxygen Combustion Process by A.A. Wells. Alan Wells was a young PhD, and he did some important heat flow calculations. He was part of his time, he was at the British, the FM committee of the British Welding Research Association, which is the Welding Institute. And actually, I haven't told you about the Welding Institute yet, I don't think. After World War II, after the Liberty ships, oh, that's the book I was supposed to bring in, the Liberty ship book. I'll have to remember to do that. After the Liberty ships failed and whatnot, there were 3 locations where they did some significant work on trying to understand brittle fracture of steel and why these Liberty ships broke up and how welding was related to that. And before World War II, they didn't really weld ships. They riveted ships, and they riveted, historically, they riveted bridges and things. The first major critical structure that was welded was the Big Inch pipeline, which was a 30-inch diameter gas pipeline from Louisiana to New Jersey. And it was built during the Depression in the 30s. And it was all welded. And obviously in a gas pipeline, you like to have the security of a welded joint as opposed to a riveted joint that might leak, right? So they decided to weld it. Actually, I go back even further. There was a guy, Comfort Avery Adams, was sometimes called the Dean of American Engineering. He was a professor at Harvard. And during World War II, he was actually an electrical engineer, and he worked on welding power supplies, among other things. And during World War II, he was put in charge of the Emergency Fleet Committee to build the ships to get the boys over there, right? Over there. Remember the song? Okay, you don't remember the song, but you might have heard it, okay? And so they had to build a lot of ships because you can't fly them over in 1917. You had to float them over. And so he was in charge of what they call the Emergency Fleet Committee, and they had to figure out how to build these ships. But no one would use welding for ships at that time because it wasn't reliable enough. People were just coming up with welding, with shielded metal arc welding electrodes and stuff. Anyway, after the war, Avery Adams decided, you know, if we really could weld these ships, we could have done things much faster in this Emergency Fleet Committee. And so in 1921, he started the American Welding Society. Okay, he was the founder of the American Welding Society. And the Adams Lecture is the biggest honor of the American Welding Society. And he gave the first Adams Lecture. In World War II, they had perfected welding enough, and the first high critical structure was this Big Inch pipeline in the 30s. And in World War II, they did decide to go with welding of ships. But welding, it was really World War II that kind of gave you the big experience with welding and welding of ships that allowed people to say, okay, we're going to weld bridges and everything else. So if you see something that's riveted, you can guess that it might be from the 1920s and 1930s. It could be from the late 40s, but sometime by the 1950s, riveting for bridges and buildings and stuff was on its way out because welding was more efficient, and we learned to do it during World War II in building of ships. In fact, there's American Welding Society often brings out this letter from President Roosevelt to Winston Churchill, where he was talking about a new welding process, which we believe was the submerged arc welding process, where he talked about how this process had dramatically improved the productivity of building ships. And we mentioned last time that you could build keel to floating it out of the bay, or driving it out of the bay, I guess the engines were running, in 2 weeks. And you could, 1 week from laying of the keel to floating it for outfitting, right? So welding came into its own during World War II, but they did have some problems. They had some defects in the welds. They had people slugging welds. Slugging welds, anybody know what slugging a weld is? I've only seen one slug weld in my life. But slugging welds, when they're welding this heavy armor plate, it was a hot, dirty job, and some people would be tired, so they just grab a handful of welding electrodes, put them in that big, deep groove of that heavy armor plate, and just weld over them. Okay? It was much easier. You didn't have to lay down all that weld metal. You just lay the the electrodes in there. Of course, if they were doing x-rays or something, you obviously would have found it, but they didn't x-ray everything back then. It's called slugging a weld, and some of the defects were due to slugged welds. The one slug weld I ever saw was some farmer up in Nova Scotia was building a trailer for a big yacht, a 40-foot yacht that was going to race in Newport, and they had to make the Y yoke for the trailer, and when they cut the channel iron, they had a gap there. They just took an old bolt and they slugged the gap with this old bolt and welded over the bolt. And the guy took the brand new trailer from Nova Scotia down to Newport, Rhode Island, won the regatta with his boat. He was driving back on Route 24 south of Boston, and he was driving along at 55 miles an hour, and he hears this bang, and then he sees this boat, looks just like his, passing him on the highway, okay? And the boat got totaled, okay? Okay, and they bring me the remains of the trailer, and here's this slug weld and brittle weld, just like Liberty ships only. So this sank another ship on the ground, okay, but nonetheless. So you don't see a lot of slug welds. People kind of know not to do it, but during World War II, a lot of those battleships and stuff had slug welds because it was a lot quicker to weld them up that way than to do it the right way. Nonetheless, after World War II, this is a long story, people wanted to understand why these ships broke up. And there were three places. A guy named Richard Weck, who was one of the most arrogant guys in the world, was pedaling his bicycle near University of Cambridge in England, and he pedaled his bicycle over to this place called Abington. I've heard Richard Weck tell the story. He's passed away now, but 30 years ago he told the story. Pedaling his bicycle up, he found this nice field in Abington. He got money from the British government, and he formed the British Welding Research Association. And the first thing, the way he sold it to the Admiralty, and we got to figure out what happened to these ships. In the United States, it turns out there was a guy named Morris Cohen here in Course 3, in the Materials Department, who had worked on the Manhattan Project, and he had good contacts in Washington, and he convinced the Navy to give him some money, along with some other people, to study brittle fracture of steels. In the meantime, the Naval Research Laboratory in Washington, D.C., and a guy named Pellini started a big study on brittle fracture of ships. And when you get to the fracture mechanics, I may actually tell part of this story in one of the other tapes. But Pellini at the Naval Research Laboratory, Morris Cohen and his associates here. Morris Cohen just passed away about 2 years ago, well into his 80s. And Richard Weck were the three guys, and those are the three institutions who really helped us understand brittle fracture of steels. And you'll hear more about that in another lecture on tape. Anyway, Alan Wells was a young engineer at the British Welding Research Institute, and in the 1980s he became the Director General of the British Welding Institute. He left for a while and came back, but he actually wrote a letter for my tenure. It's his big plan. Okay, but anyway, he wrote this article on the iron oxygen cutting process. He was a very good mathematician, a wonderful gentleman, not like Richard Weck at all. He was just a jerk. Okay, but Alan Wells was a true British gentleman, and Alan Wells, this is out of the paper, looked at cutting, oxy-acetylene cutting, and this is an old paper, and I'm not saying there haven't been 2 or 3 papers written on oxy-acetylene cutting since then. Not a lot more than that, because it's an old process that works, and people don't worry about it a whole lot, but this was probably one of the first real scientific studies. And he studied cutting, he calls it the equivalent oxygen purity, and what's on the bottom line here? The bottom is relative combustion rate, okay? So 1.0 is a low carbon, is cutting of low carbon steel. If you have Armco iron, which is very low carbon, or Swedish iron, which is also extremely low carbon, probably 10 times lower than low carbon steel. And then he has medium carbon steel, high carbon steel, razor steel. Razor steel is like over 1% carbon. It's not cast iron, but it's getting up there. And cast iron would be way down here somewhere. Cast iron doesn't cut very well. And the reason is, if you cut not pure iron, but you cut an iron-carbon alloy, you don't just get iron oxide liquid, you get carbon monoxide gas. If I get carbon monoxide gas, I now have a boundary layer of carbon monoxide. And it slows down my process. It might be a very thin boundary layer because The carbon here is very low, and there's not as much carbon monoxide as if I was doing air. Okay, I had air or a fuel gas flame for oxy-acetylene cutting, but it slows it down in proportion to the carbon content. The higher the carbon content, the slower the process, such that razor steel cuts at about 40% of the speed of low carbon, or 50% of the speed of low carbon steel. Okay, half as fast, because carbon forms an inert carbon monoxide gas, which brings back part of a very thin gas boundary layer. Now the oxygen to get to the surface has to blow away or diffuse through this carbon monoxide layer, and it slows it down. By the same token, he also took relatively impure oxygen, and he plotted it on the same type of plot. If he was using very high purity oxygen, 98% or better, he could get a relative combustion rate of 1. But if he was using 80% oxygen, he would be at less than half that speed, because you have nitrogen in that impure oxygen, and that's part of your gas boundary layer. Yes?
If you're oxy-cutting super high carbon steel, is there enough carbon monoxide formed to cause you a problem, or is it just...
Yeah. Cast iron, which is like 3% carbon, many people consider not cuttable by oxy-acetylene cutting. It is cuttable, but it's sort of like pushing liquid metal aside. I mean, it's not the nice combustion process. So if you get enough, now razor steel is hard to cut, and it would look like a lousy cut, and you'd have big slag globules. You'd lose your cut very easily. If you try to go too fast, even on a low carbon steel, if you try to go too fast, you'll outrun your combustion rate, and the thing will cool down and you lose your cut. So you have to go at the right speed, and that has to do with how uniform. I guess I passed around the little plastic thing. Okay, if you get non-uniform cuts, it's because you're not at the right speed. Yep.
Is there any damage to the ends of the
cuts?
You have a beam, you cut it down, you have this carbon monoxide gas.
Right.
Does any of that get incorporated into the end, which basically, I mean, you have your heat affected zone, but does it cause any issues with the ends of the steel?
It doesn't with steel, with low carbon steel. It could in stainless steel, and it definitely does in titanium. If you flame cut titanium, you got to grind away a 1/16 to 1/8 of an inch of that cut surface, because oxygen will diffuse in, and oxygen's bad in titanium. It lowers mechanical properties, it can cause edge cracks and things like that. So in some materials, not steel, the nice thing about steel, you form this iron oxide layer, and any oxygen that gets in there is inconsequential. Steel can, in fact, sometimes we put a little extra oxygen in steel for various reasons. So oxygen at the levels that gets in there is not harmful. You can melt right through it. Other things like titanium, you got problems. You have to grind it away after cutting.
I guess I was thinking more along the lines of, not so much are we going to end up with a sloppy cut, but are we going to cause so much carbon monoxide that you're going to breathe it in and cause yourself up? Okay.
No. Unless you're in a confined space. I mean, if a guy's inside a tank, then they're supposed to be wearing respirators, and you're supposed to have health physicists around checking everybody. And people have suffocated from the fumes from welding, but it's not carbon monoxide poisoning per se. I mean, people do check it, and if you actually tested the carbon monoxide in someone's hemoglobin in their blood after welding, you might find that, you know, there's might be a measurable difference, but it's not that their oxygen is decreased so low. I mean, a little bit of carbon monoxide really doesn't hurt you. A little bit more gives you a headache, and a little bit more puts you to sleep and you die. Okay? We're nowhere near even giving you a headache in welding. Welders don't complain, oh, I got a headache, unless they've been welding in a confined space. In which case, it's not just carbon monoxide, it's just the carbon dioxide. You're just excluding oxygen. They suffocate. Okay? Other questions? So it's not, there are fumes and gases in welding, and people study these things. More harmful in carbon welding is to use chlorinated hydrocarbon solvents. Anything like carbon tetrachloride, which you're not supposed to use anyway, but anymore. But there are various chlorinated hydrocarbons that they use as cleaning solvents. You should not weld over those, because you get a gas which has a formula of the carbon comes from the steel, the oxygen comes from the air, and the chlorine comes from the chlorinated hydrocarbon. Anybody know what this gas is called? Phosgene, one of the poisonous gases that used in World War II. Okay, so we prefer not to use chlorinated hydrocarbons and weld over wet solvents for carbon steel, because phosgene in low concentrations can harm a welder. Okay, that's a lot more important than the low levels of carbon monoxide. People have measured the ozone from welding. I mean, the arc creates ozone. In high concentrations of ozone will give you a headache. Low concentrations of ozone, that's what these things that purify the air, these little electrical air purifier, they're ozone generators, okay? And some people would say it's criminal to sell that because any level of something that can do you harm is bad, right? Well, that's not necessarily true, because pure oxygen can do you harm, okay? Congress once passed a law to eliminate anything that could measurably cause damage to DNA. You know what one of the most potent oxidizers of DNA is?
Air.
Oxygen. Okay, so Congress passed a law to eliminate oxygen from the environment. They didn't word it that way, but that was the upshot of it. Okay, good old Congress, right? Right on top of it, right?
Going back to Ethan's question about when you have your boundary layer, when you make a cut,
Yeah.
and he basically asked if the ends of the steel, if the lattice structure is affected by any of the gases getting into it.
Yeah.
And you said it's more titanium and stainless steel who are affected,
Right.
which is affected. Is that in general like most alloys? Because the lattice structure of the actual alloys.
There are some steels that have very reactive metals that might be important, but they're very exotic steels and you usually see them. And that's why you need a metallurgist. And I can't answer all questions in a general answer. In general, for the types of structural steels that we're dealing with, flame cutting doesn't affect the edges, and you don't have to do any edge prep afterwards. You might knock off the mill scale, which you'll notice on that HY80 piece, they knocked the mill scale off the piece that was going to be the good weld, because you don't want to incorporate the mill scale as slag inclusions in your molten weld metal, because inclusions can be bad. But on the backing bar, which is going to be cut off anyway, they didn't even bother to descale it after the flame cutting. Okay, if I pass this around, you'll see a black oxide on that laser cut. They don't do anything with that usually to get rid of that black oxide. It's fairly thin, and you can paint over it. It's actually more adherent than paint. It's what gives you your protection on the inside of boiler tubes. Okay, it's better than paint in many ways. So again, there are some cases if I'm going to try to melt into it, I may not want to incorporate that oxide into my molten pool because it creates inclusions, which could be harmful, but not always harmful. Okay.
How is the mill scale normally removed?
Pardon me?
How is the mill scale normally removed?
I just grit blast or grind. I mean, if you go through a sandblaster, it pops right off. Easy, just impact it off. It's a fairly brittle material, and a very thin coat like that, you'd have to bang it off pretty hard. But on a big plate cut, tap it with a hammer, it'll come popping off a lot of times. Not all the time, but yeah.
When they're welding 1-inch steel like this, or however thick, is this actually the pieces coming in kind of at an angle and then you're filling in like kind of over there, or is it start out two pieces button up against each other and the metal melts?
If I have something up to maybe an 1/8 to 3/16 of an inch, I can butt weld it at an 1/8 of an inch or a 1/16 of an inch, have them in physical contact, and I'll melt right through it with the depth of the arc melting. If it's 1/8 to 3/16, I probably want to have a 1/16 of an inch root gap. And sometimes they put little wires in there to keep, when you try to butt it up, to keep it from touching completely. Okay? Like in pipe welds, they'll put little wires in there when they butt the two pipes. If it gets a little thicker, you'll do what we call weld prep. And weld prep typically might be a 75 to 90 degree included angle here that you bevel the edges. You might use a 1/16 of an inch, what we call a flat root, and you may still have a 1/16 of an inch in here. So this would be typical size pipe, okay, that you might weld for seawater piping or boiler piping or whatever, it'll have that type of joint. If you get thicker, like 1 inch thick, then it's the same thing, but just to an extreme, because this is very small compared to that. And you actually will put multiple passes in here. You can actually see on that piece you have multiple passes. This one you can typically weld, if it's up to maybe a 1/4 of an inch, you might be able to weld in 1 pass. Particularly if you have a backing bar on the backside to catch the stuff from dripping through, okay? On the smaller stuff, surface tension will keep it in, okay? But as it gets bigger and wider, more than about 1/8 of an inch wide, it can fall through. Here.
Well, what do you have a bar that's 1 inch thick,
Yep.
let's say. You're melting it down.
Yep.
So to get the pieces to merge together, aren't you gonna end up with a narrower area than
Narrower
1 inch?
heat effective zone?
Well, no, if you've got 2 bars, you have them separated.
Yeah.
Is there something in the middle there? Because if there isn't, as you're just melting the 2 pieces of steel together, you know,
No. They will distort at an angle, and if you start out flat, they will end up V-shaped. Because it shrinks more at the top than it does at the bottom. And that's a problem of distortion. One thing you can do is you start them out cocked, and when they distort flat. Another thing you do is you just have them restrained to the rest of whatever it is, and they can't move, in which case the distortion becomes residual stresses, which if this gets to be, according to the boiler pressure vessel code, more than 1 1/4 thick, you must stress relieve, okay, to get rid of the residual stresses. Typically at about 1 1/4 inch, experience tells us that we have yield level residual stresses. The residual stresses will plastically deform the steel. Because it ordinarily would have gone like this, and you kept it down like this, so it did plastically deform the steel. The residual stresses will be on the order of the yield strength of the material at about 1 1/4 inch thick. Typically, if you're building a boiler or a pressure vessel, you will stress relieve it thermally by heating it up to 1100 to 1200 degrees Fahrenheit. They have ovens much larger than this room, and they put the whole vessel in there for a couple of hours to thermally relieve the residual stresses. Okay, as the steel heats up, it softens to about 1/2 yield strength, and you relieve the residual stresses. What do you do on a nuclear submarine, which is more than 1 1/4 thick? How do you relieve the residual stresses to prevent the brittle fracture that comes from residual stresses?
I think we have, with preheating.
No. You go on your first deep dive. First deep dive mechanically relieves the residual stresses. So don't take an undex before the first dive. Okay. Who goes on the first dive? Yeah.
They have a lottery for the hull welders.
So they have a lottery for the enlisted, or for the civil workers, but what about the leadership of the shipyard and the designers at NAVC? There's no lottery.
Yeah.
You have the honor of going on the first dive. If you are head of the shipyard, or certain heads of quality control and things like that, they get the privilege of going on the first deep dive. Okay, and some of the guys from NAVC and others. People in certain influential positions have the honor. It's not exactly an honor, it's an incentive, as they call it, right? But that's also true if you're flying some new part on a commercial aircraft, okay? I was responsible a couple of years ago for getting some approval for some turbine blades from the Federal Aviation Administration. I wasn't invited to the first flight, but the chairman of the board of the company that built the blades was on that first flight on American Airlines. So were a lot of civilians too, who didn't know anything about it. But some of the FAA people who did the approval, and some of the people who were the leadership of the company that made the blades, and some of the American Airlines executives who made the decision to put it on there. It was, they make it into a big party and a big fest, but in fact, if you really get down to it, it sharpens the mind. Make sure that you really believe in the safety of what you're doing.
Is that just an unwritten code, or?
I don't know if it's written or unwritten, but I know it's a code. I mean, I don't know if it's a written code, but it's a standard practice in many industries, and I actually think it's a very good thing myself. So, but you're right. They have a lottery for some of the people who are. So everybody in that shipyard kind of knows that they have a chance. Don't slug the welds. So, after all, if you win the lottery and you slug the weld, you might come forward. Anyway. And you might get in trouble for it too. Okay, so the point being, getting back to the boundary layers of the iron oxygen combustion process, oxy-acetylene cutting, because of either carbon reacting with carbon monoxide to form carbon monoxide, or nitrogen in impure oxygen. If your center oxygen jet's not pure, you can significantly reduce your productivity by up to a factor of 2. Wells found out that 6.2% nitrogen was equivalent to 1% carbon in steel. Okay, that's just empirical, looking at the slopes of those lines. It's all on the paper if you're interested. But 1% carbon in steel, which is not quite razor steel, but it's a high carbon steel. It's not cast iron, but it'd be like 6% nitrogen in the air. Now, I remember once being at a welding show, and these guys had a new way to get relatively pure oxygen. And basically they had these, what are called zeolites, which are these little ceramics that take a crystal structure that leaves some pretty big pores. And it turns out you can put zeolites into a pressure tank, just like a compressed air pressure tank, and you can compress the air. And if you pick the right zeolite, you will either collect nitrogen molecules or you can collect oxygen molecules in the zeolite, and so you can start to separate the air under pressure in these little porous ceramics. And if you then pump off the high pressure surrounding gas, you're left over with either nitrogen enriched ceramic or oxygen enriched ceramic. Well, they were using oxygen enriched ceramic. They would just use an air compressor, pressurize the zeolite in the pressure vessel, bleed off the nitrogen-rich air, and then seal it off, and through some other valves, take off the oxygen-rich zeolite gas, which at lower pressures it would start to outgas and whatnot. And this was going to be a cheaper way to produce oxygen on site. And so I was looking at the little display and trying to understand what was going on. I did understand what was going on. I said, how pure is your oxygen? Oh, we can get to 92%. And I said, oh, okay, well, so what are you going to use it for? Oh, we're going to use it for cutting. I said, do you realize it's going to cut your productivity by about 20 or 30%? Oh, what's that? Well, it's right there in Wells's paper, but I didn't tell him that. But I tried to explain to him about gas boundary layers, and he didn't understand that. But nonetheless, it was not a company that you should be investing in, okay? Because you need to get to like 99% pure oxygen to have a good oxy-acetylene combustion process. Don't let something sell you a 92% oxygen process, okay, because it'll slow you down by 20, 30%. However, what people usually use nowadays, because of environmental concerns of the smoke and stuff, is plasma cutting. And plasma cutting, remember I talked about diffuse flames, pre-mixed flames, and jet burners. Anybody remember what a jet burner is? I'll show you a picture of a jet burner.
Ignition is inside the constant volume.
Exactly, constant volume ignition, as opposed to ignition in the air at 1 atmosphere. So here we have a diffuse flame. Here we have a pre-mixed burner, constant pressure burning outside in the 1 atmosphere air. But if I go to a jet burner, I actually mix and ignite in the chamber, and this stuff is coming out at a much higher velocity because I got all this PDV work. Okay, it increased in temperature from the ignition of the gas, and it comes shooting out at a couple of thousand degrees or 3,000 degrees, depending on whether it's air or oxygen, pure oxygen. Now, it turns out a plasma arc is nearly the same thing. Essentially, you have a tungsten electrode, and tungsten doesn't melt, and you put it in a copper, water-cooled copper chamber, and you strike the arc between the tungsten and the copper. It's not next to the workpiece necessarily, okay? And this is called the non-transferred arc, because the arc is not transferred to the workpiece. If a portion of the current is carried to the workpiece, then it's called a transferred arc, and I'll talk about those later. But for oxy-acetylene cutting right now, which actually can be run in both modes, but let me just talk about, I'm generating the high temperatures up here at constant volume inside this chamber. And the gas comes shooting out at tremendous velocities, because the temperature here is not 2,000 degrees, it's 10,000 degrees. The electric arc has a much higher temperature. I get a much stronger jet or flame shooting out of here to melt the metal and to blow it away. So plasma arc cutting is a jet burner. It's one of the few times we use a jet burner in a welding or cutting operation, is when we use plasma arc cutting. Yeah?
Is there gas or is there oxygen that's being fueled
Well,
through there?
ordinarily it was originally pure argon or argon helium. Argon helium is not so good because the helium starts to melt the stuff up in here. So usually they would use argon, but about 10, 12 years ago, they developed something. Tungsten is not good in air because it forms WO3 oxide, which is a white smoke that comes off at 1,000 degrees centigrade. And you just see white smoke come shooting out of this, and after a few seconds you won't have a tungsten electrode anymore. They developed a process where they use hafnium, which is, if you look at the periodic table, it's almost as high a temperature as tungsten. It's 3,300 centigrade, it's like 3,000 centigrade. But the interesting thing about hafnium, the electrode is not just a simple tungsten electrode like that. They actually embed it in copper, put the hafnium as inside the copper, and this surface tip is where you get your current. But this forms a simple little layer of hafnium oxide, and hafnium oxide in a thin layer will conduct electricity. And so you can actually get your electric current through here without vaporizing your tungsten electrode. You use a hafnium electrode. Okay? And now you can run air in this. And so now for $1,000 or $2,000, you can buy a little plasma cutting torch that will cut sheet metal. And I meant sheet metal maybe up to 1/4 of an inch thick by just using compressed air as your gas flowing through. Yes, you do have to generate a gas, otherwise what's expanding, what's shooting through? They used to use argon, and they still use argon in the heavy section plasma cutter. So I have a plasma cutter in the lab that'll cut up to an inch thick, but it looks like a big old welding power supply, almost the size of that cart. But it's also generating 400 volts and 100 amps, okay? These guys with the hafnium may only be generating 15 or 25 amps, but they'll cut through sheet metal just great. It's on a little portable thing, probably weighs 20 pounds with a handle. You can plug it into 110 volts, have compressed air, and you can now cut sheet metal the speed of plasma cutting, which is faster than you can do with oxy-acetylene or anything else. So now sheet metal workers, people putting in ducting and stuff, they got these little plasma cutters. And it's all because of the development of the hafnium electrode, which will survive oxygen. Yeah.
Back in high school, you learned the definition of plasma as a charged gas.
Yeah.
Where is the charged gas and where is the arc? I kind of see a flame.
But I'm going to talk about arcs next lecture. Maybe, no, yeah, we're not going to get to it today, that's for sure. I'll talk about arcs next lecture, and then I'll go through that. Okay. I actually call it the fluorescent light lecture because that's an arc too. Okay, fluorescent light is an arc, but I'll get to that in a little bit. Now let me just finish up because we only got a couple minutes on plasma cutting, and then we think we're done with cutting. I have two pieces of plasma cut material here. This is 1/2 inch stainless steel, and if you look at the corners, you'll see this one's rounded negatively and this one's rounded positively. One of the problems with plasma cutting is if you're running straight, you get a beautiful cut, but if you turn a corner and you think about the heat transfer as you go around a radius, there's more heat on the inside radius than there is on the outside radius. And so you melt differently on the corners. So you can't get perfect corners on plasma cuts. This is a plasma cut piece of carbon steel. You can see where they drilled the first hole. They started out here, just like they did to that laser cut on the sheet metal. They started here where you're not interested. in things. You cut out and then you make a perfect circle. Perfect circle, you can make a perfect cut because there's no corners. You look on here on some of the corners and you'll see the corners are not perfect, okay? Depends on the radius of the corner. That's one of the problems. They tried to work ways around it. They did work a way around it. And I probably can't tell you the technology they worked around it. It was about to be commercialized, and because of the increased cost of certain metals, it's no longer economical. But they had a way that would cut, not with arcs, not with flames. I'll say liquid metal, okay, where they shot a stream of liquid metal at the metal. Didn't have the corner effects because you cut so fast and stuff. It would cut through 1-2 inch thick material. Beautiful cuts, beautiful edges, but it turns out with this recent increase in prices over the last 5 or 6 years of metals, it's no longer economical. So they're back to the drawing board to see if they can't come up with a cheaper metal to be the liquid, okay, that they cut with. But it's liquid metal cutting, and it's sort of an interesting technology. It's not something that's going to be a portable little thing, but in a, you know, a place where you're doing lots of plate and stuff. So people are still working on better ways to cut things. And in fact, flowing liquid metal will give you the same type of heat intensities as this 10 to the 5th watts per square centimeter that I talked about before. Okay, so you know, there are only certain things: lasers, electron beams, no boundary layers in your oxyacetylene, or a flowing liquid metal are the only things that'll give you 100,000 watts per square centimeter, or thereabouts. And so it turns out flowing liquid metal can give you even more than 100,000, might give you a couple 100,000. Starts approaching a laser and electron beam without the cost of a laser and electron beam. Almost the cost of a laser and electron beam, but not as much. But then you get into the economics, because your liquid jet of metal is expendable metal, and you can't, it's flowing out of there really quickly. And you can go through a lot of metal very quickly. And anyway, so there are technologies people are developing that will cut things even better, but just like the hafnium, the little plasma cutters and stuff. Okay, I will see you probably next month.